So good morning, everyone. My name is Skylar. I'm here with some of my group members, Jessica and Brian, and today we're going to be presenting about a novel gel electrolyte for aqueous rechargeable lithium-ion batteries. So this is the overview of our presentation, and just for some, due to some time constraints, I'm just going to skip over the specific headings. So if we could go to the next slide. So lithium-ion batteries are one of the fastest growing in the market, widely used in electronic devices such as cell phones and laptops, and it's beginning to make a splash in larger scale products such as electric cars. They have been slowly replacing other types of batteries such as nickel, cadmium, or lead acid due to their high energy density, their low self-discharge rate, and the fact that they are lightweight. So you can see in the bar graph to the left that this is just lithium demand by major product, and it was predicted upward trend from 2015 to 2020. And the pie chart on the right shows that at 37%, lithium-ion batteries are dominating the revenue market, and this was the statistics in 2009, so we expect that it has only grown from there. So I just want to go through a brief structure of the lithium-ion battery. So this is a structure of a typical lithium-ion battery, and a negative electrode, the anode, and a positive electrode, the cathode, sandwiches an electrolyte, which is the medium through which the ions are transported. As it's a rechargeable battery, it is able to go through charging and discharging processes. So during the charging process, lithium ions move from the cathode through the electrolyte to the anode. And the electrons resulting from this process move through an external circuit pathway, and the ions and electrons meet at the anode and they deposit there. This is like the charging of a battery. During the discharge process, the reverse happens, and the lithium ions go back from the anode to the cathode, and the electrons also move back through the external circuit. And this creates the power that powers the battery. So not pictured here is a separator sheet. So usually a separator sheet is within the electrolyte region, and its main function is to separate the anode and the cathode, but it is also porous to allow the transport of ions in between the electrodes. Next slide. So although lithium-ion batteries have many advantages, the technology isn't without its problems. In particular, there is serious concern regarding safety. In the case that the liquid electrolyte leaks, it can cause a short circuit which can turn off the battery, or it can cause unwanted side reactions which cause parts of the battery to degrade due to the side reactions. This can release heat, which in turn degrades other parts of the batteries, which creates more heat and creates a vicious cycle of thermal runaway. And if this keeps on happening, this can eventually lead to even the battery catching on fire or exploding. So this may not be the biggest concern in terms of small electronics such as cell phones and laptops, even though recent news stories are starting to tell us otherwise. But imagine a liquid electrolyte leaking in, let's say, a moving electric car. Obviously, the damage would be a lot more catastrophic. So, with liquid electrolytes posing such a safety hazard, researchers thought of using polymeric gel electrolytes. So, owing to their unique hybrid structure, these gels possess both the cohesive properties of solids and the diffusive transport properties of liquids. So researchers originally thought that this would be a very good substitute for the electrolyte, as it would be liquid enough in order to allow for the transport of ions, while at the same time being solid enough in order to stay intact within the casing that it is provided in. So various research teams tried this approach, and one such example is given by Chen and his research team, and they were able to make a gel electrolyte that was composed of mainly cross-linked polyethylene oxide polymers, and they were able to see initial high electrical conductivity. However, the problem with these gel electrolytes were that they stayed intact a little too well. So according to Chen, despite the high conductivity of the gel electrolytes, the rate capability of the lithium-ion cells comprising gel electrolytes is inferior to that of conventional cells, believed to be caused by the poor wettability of gel electrolytes. Now, this referred to the inability of the gel electrolyte to properly wet the battery separator, which in turn hindered the traveling of ions between the different electrodes. Although the electrolyte didn't leak out of the battery anymore, it caused some other problems due to the poor wettability. Next slide. So this is what spurred the focus of our design. So the thing is that wetting of the separator isn't just as simple as just taking a separator and pouring electrolyte on it. Due to the many small pores in the separator, it takes significantly longer for the electrolyte to, for the separator to become wet, as the electrolyte must permeate through all of the pores and overcome the different forces that exerted back onto the electrolyte. So in fact, industry data tells us that currently it takes 4 to 24 hours for the electrolyte to fully wet the separator, and this broad range is due to the fact that there are many different sizes and types and thicknesses of the separators. So with this 4 to 24 hour knowledge, we applied it to design a hybrid gel electrolyte. So we wanted the electrolyte to be liquid-like when first poured onto the separator. And we wanted to stay liquid long enough for it to actually wet the separator and be absorbed. But then we wanted it to become a gel afterwards because we would want the, we desired the gel-like properties where it wouldn't leak out of the battery. So this is why we termed it hybrid, because it's both liquid-like and it can transition into a solid-like. So defining gelling time as the time it takes for an electrolyte to go from a liquid to a gel, we wanted to optimize the gelling time such that it was long enough for the full wetting of the separator, but not too long so that even after wetting, it wouldn't continue to stay a liquid. So to achieve this, we decided to explore a property known as thixotropy. So when a gel is thixotropic, it means that when it's left by itself and it's left sitting, it is gel-like in nature. But once you apply a shear stress to it, so if you shake it or agitate it, then it becomes fluid-like and it can move freely. So if Jessica can just show, so the clear one that she's holding is just a pure liquid electrolyte, and you can see as she's moving it, it moves freely within the container. And a thixotropic solution, that one has 5% fumed silica. You can see that it's a lot more viscous. Unfortunately, it's not gelled because we kept showing it in demonstrations, so we brought it in a time where it didn't have full time to gel yet, but if you leave it, then even if it gels, even if you invert the container, it won't move at all. So the gelling time of just a pure thixotropic solution is not long enough for it to be able to wet a separator, and so we decided to modify the gelling time by combining that with a non-thixotropic polymer. So our electrolyte design comprises a thixotropic additive fumed silica and a non-thixotropic additive PVA polymer, which is polyvinyl alcohol. And by manipulating the ratio between these two additives, we wanted to optimize the gelling time. So the PVA was, we chose the PVA polymer for a lot of reasons, but some of the most important ones is the fact that it's hydrophilic. So it likes to grab onto the water that's in solution, and it also keeps the shape of our gel electrolyte intact. And also it has high tensile strength and flexibility.
So once we were able to optimize the gelling time for our electrolyte, we then had to test to see how it would work in a battery setting. And the easiest method of testing liquid electrolytes in battery settings would be to place the electrolyte in a coin cell battery. And this is because the casing and the fabrication process allows it to be a very tight and closed casing that doesn't allow leakage of the electrolyte into outside of the system. So the fabrication began with starting with a cathode cap, and then we moved on to placing a polyethylene film on top of that. And then following that, we were placing a lithium manganese oxide cathode. And in order for the battery to have an acceptable capacity, the active material, which in our case is lithium manganese, is a thick layer of porous particulate paste. And the electronic conductivity of this material is often not very high, which is why we needed the PE film, as it is a charge collector, which is typically a metal grid or a sheet. In our case, it was a sheet. And the current collector also acts as a physical support, as if we had just the paste by itself, it would be very brittle and would break in the battery. After the placement of the cathode, this is where we place our absorbent glass mat separators, and we had 2 of them in our battery design. And then this is where we placed our electrolyte to be fully absorbed into these separators. Following this, we placed our zinc anode and then our spacer to be able to put pressure on the entire system to make sure that everything was in contact. And then finally, we finished off with our welded anode cap. In addition to the industry requirement of having the optimized gelling time, there were 3 other key aspects that we were taking into consideration, which would be low corrosion, low dendrite formation, and a long lifetime. Corrosion is an undesired side reaction during electrochemical reactions, which greatly reduces the performance of batteries. Corrosion can be described as an oxidation of the metal electrodes with the oxygen from various sources, such as moisture, water evaporation or decomposition, and hydrogen evolution. Dendrite formation is also another problem with the use of a gel electrolyte. Dendrites are microscopic fiber-like structures that form on the surface of the anode and are caused by the deposition of the cations. Dendrite formation itself is not desired, but uniformity in dendrite formation can be less critical towards the battery performance. Such morphology would be that the dendrite formation would be flatter compared to tree-like growth. Finally, since the batteries are rechargeable, this means that they would need to be able to go through numerous numbers of charge and discharge cycles, which equates to the number of the times that the battery can go through its lifetime. And when you want a battery, you want it to last long, so having a long lifetime is desired. To ensure the positive thixotropic property of our electrolyte, first the gelling time needs to fulfill the manufacturing requirement, as Skylar mentioned earlier, of 4 to 24 hours of gelling time within the AGM separator before it solidifies. And to get an idea of the effect of the thixotropic effect, as you can see on here, these are our 2 vials that we demonstrated earlier, the aqueous and the gel electrolyte. So once the composition of the additives is decided, for the optimum gelling time, several characterization tests are also performed to study the key aspects mentioned earlier in the previous slide, including corrosion test, chronoamperometry, secondary electron microscopy, and Psycholife Test. Corrosion test is done to obtain the degree of corrosion on the electrodes, while CA and SEM are used to determine the amount of dendrite growth. The deposition current can be quantified with CA, but the dendritic growth is directional and is also important to study the morphology, as I mentioned earlier, as the uniformity of dendritic development can be seen on SEM. And finally, Psycholife tests are run with the battery tester so that we can confirm that the design is compatible as an electrolyte within a whole battery system. So when we were designing our gels, several additives were made into a solution as an additive to the original liquid electrolyte. The addition that we had was only about 5% throughout all of our tests, varying in the ratios of fumed silica and PVA between 4 and 3 and 1 and 2 respectively. And also with a PVA used, we had different hydrolysis percentages that ranged from 80 to 99 to 100. And one of the purposes of PVA was to enhance the dispersion of the additive in the electrolyte. And this depends on the solubility of the polymer, and the degree of hydrolysis is one of the factors that affects the solubility. Another factor when taken into consideration when creating our gels was that according to literature, a gel electrolyte cannot be obtained if more than 2% of the non-thixotropic additive, being PVA in our solution, or less than 3% fumed silica, the thixotropic additive, is used. So the first gelling time right after mixing is always higher than the consecutive gelling times afterwards. This is because not enough kinetic energy is used to break all of the bonds to allow it to take the same amount of time to gel again as it was in the first gelling time. And focusing on our industry requirement of 4 to 24 hours, within the separator, that corresponded to approximately 6 times longer gelling time in the lab. This would mean that looking for a gel with the results between 1 to 6 days gelling time in the lab would correspond to what we were looking for in industry requirements. And the best results that we were able to get would be our Electrolyte C, which gave us 3 days, and then the second time gelling time of 1.5 days. And the composition of this was 4% fumed silica and 1% of 99% hydrolyzed PVA. The corrosion test is done by measuring the current with a range of voltage. The left side of the curve represents the anodic current, and the right side represents the cationic current. This implies that the equilibrium is reached when the current reaches the peak at the bottom on the graph as seen above. And by using the TOEFL analysis method, the corrosion current was also determined. And the lower the current, the less corrosion that occurs. The corrosion current is shown to be reduced more than 50% with the addition of fumed silica and PVA compared to that of the liquid electrolyte, and the gel electrolyte with only fumed silica as well. The currents are converted into a corrosion rate to give an idea about the degree of corrode using the equations, where EW is the equivalent weight, D is the density of the electrode, A is the surface area, and K is a constant to convert the current into corrosion dimension per year. CA is an established method to determine whether dendritic formation has occurred on the electrode. An overpotential is applied to force zinc deposition on the working electrode, in our case would be the zinc electrode, to determine the type of deposition, whether it's dendritic or not. The current density can be plotted against the time to determine whether or not dendrites have formed. The plotted curve will first experience a decrease in the slope as the current stabilizes, but will reach an equilibrium after a certain period of time. The higher the absolute value of this current density after reaching equilibrium is more likely that deposition of dendrites will occur. And the lower the absolute value would be the opposite, where we will have a more smooth surface. Literature shows that the absolute current density for a reference electrolyte is currently in use is approximately 20 milliamps per centimeter square. Thus, an absolute value lower than 20 milliamps per centimeter square would have a better dendritic formation. And with our design, it was approximately 60% smaller than the liquid electrolyte in dendritic formation. But as our results showed, our design electrolyte showed a significant decrease, but not as good as 5% silica. But even with these results, the CA test is not enough to determine whether or not there's formation, because there is also the orientation and uniformity of the dendritic deposition, as I mentioned earlier. Thus, we had to use SEM in conjunction to allow a qualitative observation of the dendritic formation. If the deposition results in an even and smooth surface, this means that no or little dendrites have formed on the surface. And if the deposition is uneven or comprises of flakes and or other types of uneven growth, this means that dendrites have formed and will act to gradually destroy the battery's performance, as it results in a non-equal distribution of the electrolyte and potentially can cause a short circuit. So as you can see in the SEM images above, the first one we have is our reference electrolyte at 250 times magnification. And even at such a low magnification, you can see that the dendrites are quite large and they form island-like shapes. These island-like dendrites tend to protrude off of the surface normal to the plane of the anode, directly connecting to the cathode. This type of growth will be very fast and cause short-circuiting at a much faster rate compared to the other ones. If you take a look at the 5% fumed silica anode at 1,000 times magnification, you can see that the type of growth is actually flake-like. With this, it causes a more of a amorphous growth and requires more deposition for the for the electrode to be able to create a short circuit. Now, if you take a look at the last image, it's our electrolyte C at the same magnification as the 5% fumed silica. But as you can see, the feature sizes are much smaller. They're still flake-like, but the deposition is a lot better, and it can be seen that our dendrite formation is more uniform.
Another test that we performed is Psycholife Test. So because it's a rechargeable battery, ideally we want it to charge up to the same capacity, but obviously it doesn't in reality. And so we had to run some Psycholife test using the electrolyte in a battery system. And so each cycle was charged at the rate of 1 C, which is equivalent to charging at the current of so that it takes an hour to charge, and then just discharging at 1 C as well. So we did this cycle 150 times for the liquid electrolyte and our designed battery, designed electrolyte and the fumed silica. But for fumed silica, we couldn't even fabricate it because it was too thick to be observed in the glass mat. But the result between the liquid electrolyte and our the additive, with the additive, it shows similar performance of charging and discharging capacity. So in conclusion, we controlled the ratio of the components in the additive, and we could optimize the gelling time that's required for the industry. And also we greatly reduced the corrosion and dendritic formation compared to the liquid electrolyte. And also the cycle life, the performance was maintained. So for future application, because we have optimized the gelling time, this means that we can apply to different scales. We can apply to smaller scales such as cell phone or even larger scales such as automotive batteries. Another potential area is solar cells. Some solar cells use very similar electrochemical system as battery, but then they also have liquid electrolyte that also has spill problem or other leakage problems, and we expect that this gel electrolyte could help to solve these problems. Thank you.
The CA.
Yeah, to decrease the date, right?
Cycle test?
Yeah. The cycle life.
Yes.
Oh, Psycholife testing.
Yes.
You can figure.
Sorry.
That this one.
Yeah.
To do decrease, continue to make the cycle number. If you go further, 150 cycle, keep decreasing, right?
Yeah.
Well, the thing is that, so 150 cycles, it's definitely not adequate to say that the trend will keep going the exact same way. When we were studying, so we only got up to 150 cycle numbers, but for previous compositions, because we were able to run it for a longer time, we saw up till, I think, 1,000 something cycles, and it was seen that it fluctuated sometimes, so it kind of crossed over, or let's say, for example, our reference, the pink one, it decreases at that rate, but the reference electrolyte, even though it seems to be doing better, could suddenly do worse as well. So even if our trend for our sample keeps going the same rate, we can't tell whether the reference electrolyte will keep on staying the same. And I think that our goal was sort of to show that our electrolyte can do almost as well, if not better, than the reference electrolyte. So we would have to, actually our cycle tests are even going on right now, so we would have to further analyze to see if the trend changed between the two. But for now, I think the best we can say is that they're similar, so we know that it's at least doing what we want it to do. Right.
Yeah.
Yes.